two equations and two unknowns. Well, this is quite easy, right? We're all used to this. But what if we add more? Yeah, we're gonna need an algorithm. Luckily, already one exists. It's called Gaussian Elimination. But at one point in time, this didn't exist, right? Let's go back to that time. I think you and I can actually reinvent this from scratch. And that's what we're gonna do today. So this is a huge task, right? If we're even going to have a chance, we need to start with examples. Let's start with the most simple possible example. The humble 2x2 system. Let's do this. So we can probably learn something about the way we solve this, which we can probably generalize. Well, I like to do this by eliminating one of the variables in the second equation. So this 3x term, I want to eliminate that. How? Well, I multiply the first equation by something and add the two equations. And you can see we're going to eliminate the 3x term. Now, we don't need the first equation to be scaled anymore, so I'll just divide by 3 again. And now this second equation, we don't need it either. It's done its purpose. We can just replace it with this third one. So we have something which is a lot simpler. We've eliminated a variable in the second equation. That thing is probably going to come up a lot. So I just want to standardize the move that we did, the operation we did to go from here to here, just to eliminate a variable. We've done a few things, right? We've added equations, scaled equations, replaced an equation in one go. Maybe I should actually quantify this as a single operation. Equation replacement. We've replaced equation 2 with equation 2 plus 3 times equation 1. We can even put some notation for this, where EI can be equation I, representing equation I. So this would be equation 2 maps to equation 2 plus 3 equation 1. Equation replacement is probably going to come in handy a lot. This is definitely a breakthrough. Now, can we reduce the amount of writing we have to do? I don't really want to write more than I have to, right? What actually matters here? Is it the x's and the y's, the plus or the equal sign? I don't think so. It's probably just the numbers itself, the coefficients, and also the right-hand side of the equations, right? What if we just keep the numbers themselves? Because then that's all we need, right? You can go back between these and you can kind of see what they mean. Each row represents an equation and each column represents a variable. The first column is the x column, the second is the y column. And now we're dealing with basically kind of like a matrix, okay? Rows and columns. So maybe instead of equation replacement, I could call that thing row replacement, that operation I just talked to you about. In fact, we'll call these two things row operations. These are the main ones to kind of note. Scaling a row and replacing a row. Scaling is, well, we can't scale by 0, that's the only thing, but otherwise scaling a row is not a problem. That's not going to change any solutions. And replacing a row is also not going to cause any problems to the solutions, right? All we're actually doing is adding and scaling stuff. Okay, let's do another example. So we have these two equations, and I'll write this in matrix form, first of all. We want to eliminate this 3, right? Because we want to simplify the second equation. And the way we eliminate it, as you've seen, is by doing a row operation using the first row. Okay, so we'll probably do R2 maps to R2 minus 3 over 2 R1. Yeah, I think that works. And I think you actually get all zeros on the bottom row if you actually do that. Okay, so this is our new matrix. What on earth does this second row mean? 0x plus 0y equals 0. 0 equals 0 is basically what it's saying, right? That doesn't help us at all. That's always true. Only the first equation is actually giving us information about x and y. We can't solve for x and y, like we can't get actual numbers, but we can solve for x in terms of y. And y can actually be anything, any real number, or even complex if you really want to, but any real number, I guess. So there's infinite solutions here. Maybe it was caused by this full 0 row appearing in our matrix. This other example, let's look at it quickly. So we have this matrix, and we'll do the row operations to eliminate the 2, okay? We'll do this row operation, and we actually get 0, 0 minus half. So that means 0 equals minus half, which is not true. So what on earth is happening here? We've been led to a contradiction because of this, well, contradictory row in our matrix. So I think there's no solutions to this system. Row operations do not change the solution set. All row operations are doing are adding and replacing and scaling, which don't cause problems, right? So this must mean the system itself is is flawed or it's inconsistent. There's no solutions. And it was caused by a contradictory row appearing. This could be a breakthrough. Contradictory rows appearing in the matrix might be equivalent to saying there's no solutions. I think that's kind of important to note. Time for a quick recap. So what we've learned from this 2x2 expedition is abstracting the problem to a matrix is pretty genius. Row operations are overpowered, mainly the replacement one, row replacement, because that helps you eliminate a variable in an equation in basically one go. And that idea of eliminating a variable in an equation simplifies that equation, right? That's the main idea what we're trying to do. And as for the nature of solutions to a system, we've encountered a few different ones. No solution, infinite solutions, unique solution. I'm not so sure what about the form of the matrix indicates unique solution yet. But yeah, there still are a few questions to be answered. Let's look at a 3x3 example and maybe we can extend our current algorithm. We want to eliminate the x coefficient in row 2. So we'd use a row operation of this form, right? Where we choose the number k. But whatever we choose for k, well, k times 0 is still going to give us 0. In other words, any row operation we do is not going to eliminate, well, the 1 in the entry. It's not going to eliminate it, it's just going to keep it the same. So this isn't going to work. Previously, we didn't have this problem. The top entry was not 0, and so we could do row operations to eliminate below it. We could just, well, reorder the equations. In other words, we could swap the rows. I guess swapping two rows might even be a row operation we didn't think about before. And this way we do have a non-zero thing on the top, and we can proceed as normal. This non-zero entry seems to actually be quite important. I'll call it a pivot. I think that's a pretty intuitive name for it. Bruh. Okay, anyways, so let's make this first step choosing a pivot in the first column and swapping it to the top. But the thing is, there might not be such a pivot in the rare case when we have zeros everywhere in a column, I guess. So maybe I'll just say in the first column, which is not all zeros. I think if you have full 0 columns at the start, you just skip them probably. Okay, anyway, now let's try to do step 2. I'll just reword this actually. To be more general, we'll use row 1 to eliminate entries below the pivot. I think that'll be more general, right? So let's do that here. We don't need to do it for row 2 because it's already done. It's 0 already. So we do it for row 3. And we are finished with this step. Now step 3 needs to be changed, right? Solve for y in the now trivial row 2. Well, row 2 is not trivial. But it is simpler because we've removed a variable. In fact, row 2 and 3 together, they make a 2x2 system. So we've basically reduced our much larger problem to a smaller sub-problem. What if we now use our algorithm on this sub-matrix, which is smaller, right? It's much simpler. This might actually be a huge breakthrough. We can solve this whole thing with recursion. Yeah, let's actually try this and see what happens. Let's do this. We choose a pivot, right? On this sub-matrix here, we choose a pivot. It'll be this guy. And we swap it to the top. That's done. We use row operations to eliminate below it. And we have now a smaller sub-matrix. Well, this one is a bit of a joke. There's not really anything to do here. So I guess we just skip this step. We've reached something trivial. So now we just have to substitute stuff. This last equation now is trivial. Z equals 7 over 2. And we get a few other equations, and you can actually see that we can solve for all of them. We get a unique solution. Recursion might have saved the day. Okay, so we got a unique solution. I'm just saying, imagine you had a huge matrix and you just want to know, is there a unique solution? Well, you're not going to back substitute, right? That's going to take forever. Can you just look at the form of the matrix and tell? That's what I want to know. Notice how, if you look at it by rows, the pivots are the first non-zero element of each row. In other words, to the left of the pivots are always zeros. You can see that, right? Another thing I'm noticing just in general is they form a downwards pattern. I think this downwards pattern is important. We'll probably get back to it later, but this could be a breakthrough. So our current method is essentially this. The dumbed down version is this though. You just eliminate entries below a pivot and you get a smaller system just by doing that, and you just repeat on that system. Recursion actually might be overpowered. Okay, let's actually try to figure out more about this final matrix form. It seems that the final matrix form can actually tell us about the nature of solutions. I'm not sure about the infinite solutions part. Is it possible that you can have infinitely many solutions and no zero row? Let's try to make an example, maybe with a non-square matrix this time. Using our method, we choose a pivot, and then, well, this step is a bit trivial in this case. Now we use row operations to eliminate below the pivot, and we get this submatrix, which is, I guess, trivial, right? There's not really much else to do. I could probably change this word trivial. It's a bit too vague to say having one row. I think if it has one row, then we can skip the step. And now we just substitute, right? These are our two pivots. And so we get this equation for y and z. We know y in terms of z now. But how about z itself? We don't know anything about z itself. Nothing is telling us what z is in terms of its value, right? Only thing we know is x and y in terms of z. Okay, infinite solutions again, because z can be any number, right? Because changing z, that would just adjust x and y. But z itself can be anything. Okay, we've got infinite solutions, but no full zero row. I guess the counterexample did work. What I'm noticing is when you have a pivot in, for example, the x column, okay? The pivot in the x column basically helps you write x in terms of the following variables, y and z, or at least one of them, right? So this idea is having a pivot in a column determines that variable in terms of the following. So if the following variables are fixed, that pivot variable is completely determined. Do you get the idea? Now, let's try to reason why a non-pivot column corresponds to a free parameter appearing. Because that's what we've seen. The z could be any number. Imagine this is just one part of a matrix, okay? I wouldn't say it's the full matrix, just a part of it. Well, this would be a non-pivot column. There's no pivot in this column. And maybe we should label these with some variable names. The only equations involving this xk plus 1 are those that start with previous pivots, with xk minus 1, etc. So as long as xk plus 1, if we fix it to be anything, the previous variables are basically determined, at least for xk plus 1. But xk plus 1, we can't write it in terms of any following variables. Nothing pins it down and says xk plus 1 has to have this restriction. So I think we can take xk plus 1 to be any number, and then the previous variables are determined in terms of it, and it works. There are definitely infinite solutions in this case. As long as you get this sort of non-pivot column, you get a free parameter and therefore infinite solutions. That seems to be the case. We could even look at another example. I'll just speed run through the row operations. But you get a zero row here. And then you can clearly see we do actually have a non-pivot column here. It definitely seems like infinite solutions is equivalent to saying that you have a non-pivot column. And at least there's no contradictory rows. That should also be included. And I think it makes sense to say that unique solution is equivalent to saying that all columns have pivots. And also that, well, you don't have any contradictory rows. Now, I want to know what are some defining features of the final matrix form. Now, one thing we've noticed is the pivots form a downwards pattern, right? So why is that? It's definitely to do with the submatrix step. Imagine this is a pivot, then the next submatrix will be this green one here, right? The pivot will come from here, the following pivot that is. And it will be somewhere in this row because we always swap the pivot to the top of each submatrix. Remember that step? So we do actually get a pivot on the following row. We can repeat this logic and we basically get the idea that each pivot is to the right of pivots in higher rows. Take a moment to digest that, okay? So we've talked about rows with pivots. How about rows without them? Those are basically zero rows. So we've seen before that zero rows seem to end up at the bottom, but imagine that that didn't happen. Imagine you have a zero row and below it is a pivot row. The reason this thing can't happen is because if you consider this submatrix, in our algorithm, we would have swapped this pivot row above. This wouldn't have happened at all. So what actually ends up happening is all the zero rows accumulate at the bottom and all the pivot rows are going to be above that. So we'll define this as the row staircase form. It's a bit of a weird name, but it kind of makes sense, right? And it has these two conditions for it to be defined. Firstly, I'm going to name this algorithm in honor of Gauss, the mathematician. Bruh. We'll call it Gaussian Elimination. Now, I'm going to rename this row staircase form that we discovered to something called row echelon form. Echelon just sounds way cooler, and I've looked it up. I found a good replacement for staircase. Let's just call it that. Bruh. A matrix is in row echelon form as long as you have 0 rows at the bottom and the pivots have this sort of downwards trend, right? Now, some definitions to note that we've been using pivot, right? First non-zero entry of a row. But I'm going to rename it to leading entry because that kind of makes a bit more sense. Leading entry of a row is the first non-zero entry of that row. So I'm going to call it leading entries. Therefore, everything hinges on leading columns and non-leading columns. As for nature of solutions, a contradictory row appearing in the row echelon form means no solutions. They're equivalent. No contradictory rows, as well as all columns leading, which means all columns have a pivot, that means we have a unique solution. And suppose we have a non-leading column, then infinitely many solutions. Now, how about cases where you have exactly a finite number of solutions, but more than one? Is that possible? Well, I'll let you figure that out. I think you can do it. You could have discovered this all by yourself. That's what makes Gaussian elimination so special.